The vapor pressure of a liquid at a given temperature is the value of the ambient pressure below which the liquid would begin to boil at that temperature. In other words, it is the external pressure that must be exerted on the liquid to keep it from boiling at that temperature. Shown here is a curve of the vapor pressure for water in kilopascals versus the temperature in degrees Celsius. Notice that the pressure axis is logarithmic to more clearly show the vapor pressure value at lower temperatures. Furthermore, notice that the vapor pressure at a temperature of 100 degrees Celsius is equal to about 101 kilopascals, which is the standard atmospheric pressure. In other words, when water is subjected to a 1 atmosphere ambient pressure, it boils at a temperature of 100 degrees Celsius. Finally, notice that the curve ends at a temperature of 373.99 degrees Celsius, which is equivalent to 647.14 Kelvin. This is the critical temperature of water, beyond which the liquid undergoes a smooth transition into a gas, instead of the abrupt phase change that is characteristic of boiling. The vapor pressure versus temperature curve on the phase diagram of a substance is the curve that separates the liquid region from the vapor region on the phase diagram. Notice that by decreasing the ambient pressure, we can decrease the temperature at which the substance boils, and that by increasing the ambient pressure, we can increase the boiling point of the substance. Boiling point depression is the lowering of the boiling point temperature of a substance as a result of a decrease in the ambient pressure. Water boils at a temperature of 100 degrees Celsius at sea level, where the ambient pressure is about 101 kilopascals. On the other hand, at the top of Mount Everest, where the ambient pressure is about 26.4 kilopascals, water boils at a temperature of only 69 degrees Celsius. This phenomenon is responsible for the fact that it takes longer to cook food in an unsealed container at high elevations. Shown here is an experiment in which we measure the internal pressure and the internal temperature of a sealed enclosure. Water can flow into the enclosure through a small hole in its bottom. The pressure within the enclosure can be lowered using a compressor that can suck air from the enclosure. By decreasing the ambient pressure using the compressor, while keeping the temperature constant, we can get the water to boil at room temperature if the pressure is low enough. We start by introducing a small amount of water through the hole in the bottom of the enclosure. Then the compressor is turned on and sucks air from the enclosure. Notice how the pressure that is read by the pressure gauge on the right is decreasing, while the temperature value from the thermometer on the left remains the same. Finally, notice that at a low enough pressure, even though the temperature is still constant at room value, the water boils. The water continues to boil until it all turns to vapor and disappears. The pressure cooker is a sealed cooking vessel that does not allow air or vapor to escape, except at a preset pressure that is higher than atmospheric pressure. The higher pressure generated within the pressure cooker allows the water within it to boil at a higher temperature than 100 degrees Celsius. The higher temperature allows cooking times to be reduced by up to 70%. The pressure cooker is equipped with a pressure regulator that relieves the steam pressure inside the vessel at a preset pressure value. This is a safety feature that prevents the pressure cooker from exploding due to too much pressure buildup inside it.